Look straight up on a clear day. Your brain tells you you're staring into empty space. But if that sky were empty, Earth would be a silent, frozen rock, totally exposed to lethal radiation and high-speed debris of the cosmos. What you are actually looking at is a heavy, dynamic blanket. It's a highly pressurized mixture of suspended dust particles, liquid water droplets, and circulating atmospheric gases, all physically chained to the planet by the pull of gravity. This pie chart breaks down our atmospheric composition, and it reveals a surprising lack of diversity. A massive 99% of dry air consists of exactly two gases, nitrogen at roughly 78% and oxygen at 21%. Nitrogen completely dominates the mixture, doing heavy lifting behind the scenes. First, it dilutes the oxygen. Without nitrogen, a single spark would cause fires to burn violently out of control. Second, specialized soil bacteria pull this nitrogen directly from the air and convert it into the base proteins that support the entire global food chain. The air we walk through every day is a dense, highly active chemical ocean. It actively engineers the biological conditions required for us to survive. Let's begin our ascent. Rising 13 kilometers, we enter the turbulent troposphere, where all weather happens. The remaining 1% of trace gases live here. Heavy carbon dioxide sinks to the bottom, fueling plant photosynthesis and trapping escaping heat to drive the greenhouse effect. You also find highly specific trace gases here, like radon. Scientists are tracking sudden spikes in ground-level radon concentration right now as a potential early warning system for earthquakes. Gases are only part of the mixture. The troposphere is loaded with non-gas elements, specifically water vapor and microscopic dust particles. We tend to think of dust as an irritating impurity, but its presence is absolutely mandatory. Dust serves an optical function. When incoming solar light hits these suspended particles, the blue light scatters across the sky. Without floating dust, the daytime sky would look exactly like the pitch-black void of deep space. Dust also acts as a hygroscopic nucleus. A hygroscopic nucleus is a solid microscopic particle that provides a surface for condensation. Water vapor cannot spontaneously form a raindrop on its own. It clings to this solid, jagged surface to finally condense into liquid water. As we climb higher through the troposphere, we experience the normal lapse rate. The normal lapse rate is a meteorological rule stating that for every 165 meters of altitude gained, the temperature drops by exactly 1 degree Celsius. This predictable freezing mechanism is why mountains are permanently capped with snow. The troposphere operates as a heavy, pressurized engine room. Trace gases, suspended dust, and steadily dropping temperatures align to manufacture Earth's weather and climate. Pushing past 13 kilometers and climbing up to 50 kilometers, we enter the stratosphere. The turbulence stops entirely. The air is perfectly calm, completely devoid of weather, making it the ideal cruising altitude for commercial airplanes. Look at the temperature profile here, and you'll spot a massive anomaly. Instead of continuing to freeze as we move further from the Earth, a dense band of ozone molecules causes the temperature to suddenly rise. That ozone acts as a planetary sunscreen. It violently intercepts incoming, deadly ultraviolet radiation from the sun. The chemical reaction absorbs that lethal energy and converts it directly into localized heat. Leaving the ozone behind, we ascend from 50 kilometers to 80 kilometers into the Mesosphere. Without the ozone to trap heat, the temperature rapidly plummets to a bone-chilling minus 100 degrees Celsius. This freezing layer performs a highly violent function. When incoming meteors hit the Mesosphere, the extreme friction of these frigid gases instantly incinerates them. What we call a harmless shooting star is actually a massive piece of space rock burning to death in the Mesosphere. The troposphere creates the conditions for life, but the stratosphere and mesosphere act as planetary body armor. They systematically neutralize radioactive waves and physical cosmic impacts long before they can strike the surface. Moving past 80 kilometers, we enter the ionosphere, also known as the thermosphere. The air here is incredibly thin, and it takes the absolute full, unfiltered brunt of the sun's raw energy. Temperatures skyrocket once again. That intense solar radiation violently strips electrons away from remaining gases. This creates ions, fields of highly electrically charged particles floating in the upper atmosphere. This diagram illustrates how humanity exploits those charged particles. Specific sublayers in the ionosphere act like a giant, invisible mirror. We bounce our radio waves off these charged ceilings, reflecting them back down to Earth to enable long-distance global communication. Finally, pushing past 640 kilometers, we cross into the exosphere. This is the absolute outer limit, where the last traces of Earth's atmosphere slowly bleed out into the vacuum of space. Only the absolute lightest gases, hydrogen and helium, survive at this altitude. The particles drift miles apart without ever touching. This near vacuum provides the frictionless orbital paths for our GPS and global weather satellites. At this extreme upper edge, the atmosphere stops facilitating biological survival. Instead, it serves as fundamental scaffolding for global connectivity and modern human technology. Let's fall back to Earth. We drop from the satellite-filled exosphere, tear through the glowing electrical mirror of the ionosphere, plunge into the freezing meteor shield of the mesosphere, pass the calm radiation sunscreen of the stratosphere, and finally splash down into the stormy, heavy troposphere. We are looking at a highly specific functional stack: a communication mirror, a physical shield, a chemical sunscreen, and a pressurized weather engine held in perfect alignment by gravity. Every single percentage point of trace gas, every microscopic speck of dust, and every sudden temperature inversion executes a specific, irreplaceable job. The atmosphere is a highly precise, fragile piece of planetary engineering. It takes this exact sequence of gases and temperatures to carve out a pocket of life in an otherwise hostile universe.